wouldn't it? I mean, wouldn't it only make sense that you know, math is kind of like building blocks. So if we added pieces, it would have the same pattern. It'd follow the same kind of technique. In other words, if I had something like this is actually number 50 from your homework, if you want to label it like that. We have a plus 2 times a squared minus 3a plus 7. Once again, the idea is just to multiply every single piece to every other piece. So we have a, we'll share it over here to everything. Let's see, a times a squared gives me, okay, a times negative 3a gives me that, negative 3a squared. And then a times that 7 gives me a positive 7a. Okay, are we done? No, we have to take the 2 and share it now, because we're making sure that everything hits the other polynomial. So a squared times 2 gives me a positive 2a squared. Good job, Misha. Then we have 2 times negative 3a going to give me, okay. Then we have 2 times 7 going to give me 14. Oh, and now we're back to the old stuff that we learned the last time. Put like terms together. Have fun with that. Do I have any other a cubes? No, so I'll try a cubed. Any other a squared? Sure. Okay, so the 3 plus a 2 gives me, what? Negative 3 and a positive 2. Okay, negative 1a squared. You don't have to write the 1, remember. You could have just written negative a squared. Now we have 7a minus 6a. What's a 7 minus 6? Plus 1a, and a 14 left over. So a cubed minus a squared plus a plus 14. We still doing okay? If you were able to survive this one, I mean, seriously, I guess I could give you 3 times 3. Would it change anything? No, you take the piece through the other one, the next piece through the other one, next piece through the other one. Okay. That's as hard as it can get. Just takes longer, yeah. Now, there is one type, okay, that you can, at this point, you could do with your eyes closed, but there's a shortcut associated with it. So I'm going to show it to you like twice, two of these easy examples, so that you can maybe see the shortcut. And, yeah, that's the idea for tonight. We've got it. Like I told you guys before, I don't think it's too hard, but when you get your homework, if it is, ask me questions and we'll figure it out. We'll start to see what's going on. Here's the deal. Look at something like, excuse me for making funny sounds. I'm thinking, let's say 2 minus x times a 2 plus x. I'm kind of curious. Maybe there's a pattern here. I mean, these look very similar, don't they? Yeah. The only difference, we have a 2 and an x and a 2 and an x. The only difference is one of them has a minus in between, and the other one has a plus in between. So similar, it's almost irritating. But let's multiply it out and see what happens. And I bet if we find this similar, maybe we can find a pattern. So I'm going to say, you guys can do the FOIL if you want. Do you like FOIL, or do you just like the sharing everything idea? Some of you guys learned FOIL? Okay, let's write the FOIL. First, so 2 times 2 gives me, okay, 2 times x for the outer gives me positive 2x. For the inner, we have a negative x times a 2. And for the last, a negative x times a positive x. Let's see, a negative times a positive is a negative. And then we have x squared. Okay? So that's 4 plus 4x minus x squared. Let me write it this way. I'm going to write it in order, like we see polynomials a lot. That was probably a hard one to start with. Okay, let's do another one. Let's say we had x plus 3, x minus 3. So once again, we have a similar pattern happening. We have, let me rewrite that.
Where do you get that 4 plus 4x?
Huh? Yes, it would. I'm so glad you guys point that out. That would change the entire situation. Because actually we have 4 minus x squared. Thank you. I'm going to actually leave it like that. That makes us see the pattern better. Good thing you guys are paying attention. Thank you, everybody who yelled at me just now. Okay, so FOIL. X times x on the right-hand side gives me x squared. Within the FOIL thing, or multiplying every piece together. Outer, we have a negative 3 times an x. That sounds like negative 3x. Inner, we have positive 3 times x. Same kind of situation happening. And then a 3 times a negative 3 gives me negative 9. Oh, so actually that thing that Kel pointed out, the mistake I made was a pretty big one. Because what just now happened again? Those canceled. Okay.
So this is the same thing as the x squared and both sides of 3, so it's the same.
It looks kind of like it, doesn't it? If you have a plus and a minus, every single time those middle pieces are going to kill each other, aren't they? Which means that if I just look at the first piece, and in the first example, my first piece was, let me get the highlighter out. My first piece was the 2's. If I take the first piece and square it, I get a 4. Okay, that's good to see. But that is the same thing as a 2 squared minus, and then same thing for the x's, right? X squared. Let's look over here and see if that pattern is going to be consistent, because that'd be a really, really powerful thing for us to notice. Again, we have a plus and a minus. Do I get, when I times x, do I end up in the final answer with an x squared? So the order matters, doesn't it? Okay, that's important. The x's start off first up here, and down here they're first, x squared. Then 3 times 3 gives me negative 9, or the 3 squared you can think of. 3 squared, x squared. So it's the first stuff that matched squared, whenever the stuff is so similar, minus the second set of stuff squared, right? Nice. But these, again, are really, really careful. You have a plus and a minus. They don't match. They're opposite on the inside. That's what's making the middles cancel and give you 2 pieces. Good. These are very, very special. When you start factoring, which in this class we're going to start some basic factoring. We won't teach you this part. So when you start factoring, these are considered perfect squares. In other words, to factor, you'd say, oh, look, that's going to be, when I break it down, I'm going to have a 2 in both sets and an x in both sets. And I'll put a plus and minus in the middle. Difference of perfect squares is what it's called. I'll write this. That way when you have your notebook out in 080, you'll be ahead of your classmates. What we're getting here is called the difference of perfect squares. Because here, you have a perfect square minus a perfect square. If you were going backwards, you're just getting whatever times itself, right? And the x's with plus and minus. Same thing here, difference of perfect squares. So a minus in between 2 squares, you're getting the x's and you're getting the 3's, because 3 times 3 gave us 9. Very powerful. Soon you'll care very much about that in your next life as a math student. But the next pattern I want to point out to you is also a pretty powerful one. Not as cool as this one. I'm going to have to be straight with you about that. But it's still a good property. The idea is that there's still a pattern if they did have the same sign in the middle. So if I had something like x plus 10 times x plus 10, where they're actually the exact same. So notice in this time, we don't have the minus and the plus. Stuff's not going to cancel. There's still a pattern to what's going to happen. They match exactly. Stuff's not going to cancel, but something similar will happen. Okay, so when we FOIL this thing, we get, let me write the word FOIL for visual people. X times x gives me Okay, 10 times x gives me 10x, and the last 10 times 10 gives me That's interesting, isn't it? Oh, wait. Did I lose one of my 10x's?
Yeah.
Sorry, guys. I'm trying to. Okay. We actually have another 10x and 100. And now it's even more interesting. Let's combine these so we can see it better. 10x plus 10x gives me. I didn't mean to not do the enter. In that foil. Okay, so now we have something like this. A nice trinomial, right? But look at your original and see if you guys see something. This is mostly for fun. Again, you could have done it without seeing the pattern. You know how to do the work now. So this is something to help you out later in math. If you're looking at this thing that was repeated, the first piece, it just got squared, didn't it? The last piece, it just got squared, didn't it? What about this piece? It's like it took them and multiplied them, 10x, it put them together, right? 10 times x. And somebody said a key word. They said double. Yeah, because there were two of them. See? 1, 2. That's why it's always going to double. So that should be the pattern, shouldn't it? You'll always have 2 times whatever those two pieces were, a 10 and an x. Very cool. This is called the perfect trinomial, I think. Hold on. I'm blanking out for who knows why. This thing is above considered perfectly square also, just in a different way. So here, let me highlight it for you. That's right there is something you should notice. Anytime you see a relationship where you have a perfect square, like x squared in the front, and a perfect square at the end, if you ask yourself what squared, that's a 10 squared, that's an x squared, if that's doubled in the center, this is really easy and really fast to go backwards on. Because you know it was just the same thing twice. You'll learn more of that again in 080. But that's a cool pattern to see for today. Okay, we're done with lecture, so let's take a 2-minute break, and when you come back, we'll have some homework time.